A nuclear power plant can cost more than $30 billion to build. And that creates a strange question. How can anyone possibly make money owning one? The answer becomes even more confusing when you look at what happened in Georgia. Plant Vogtle was supposed to become one of America's newest nuclear power stations. Instead, its two new reactors became one of the most expensive power projects in U.S. history, with total project costs reaching roughly $30 billion, years of delays, billions in additional costs, and a construction process that became a financial nightmare. Yet the reactors were eventually completed, and now they can produce electricity for decades. So was spending tens of billions of dollars actually a terrible investment, or is nuclear power one of those businesses where the economics only become visible after you look far enough into the future? To understand that, forget the image of a nuclear plant as simply a giant machine. Think of it as a financial asset. You spend billions before earning meaningful revenue. You borrow money for years while construction is underway. You maintain an enormous workforce and thousands of specialized components. You operate under some of the strictest regulations in the world. And then, if everything works, you have an asset capable of producing electricity around the clock for decades. That is the nuclear business. And the first thing that makes it unusual is that almost all of the financial pain comes before the plant even opens. Imagine deciding to build a new reactor. Before the first megawatt hour reaches the grid, you may need land, engineering, permits, environmental studies, construction crews, specialized equipment, cooling systems, turbines, generators, transmission, infrastructure, safety systems, security, and an enormous amount of financing. The reactor itself is only part of the story. And because construction can take many years, the owner has a problem that most businesses never experience at this scale. The investment is losing money before it has even become a business. This is called construction period financing risk. If the project costs $10 billion and takes 8 years, the owner isn't simply waiting 8 years to receive revenue. Interest is accumulating. Contracts are changing. Workers need to be paid. Materials become more expensive. Regulations can evolve. And every delay pushes the revenue date further into the future. That means the true cost of a nuclear plant is not simply the price of concrete, steel, turbines, and reactors. It is also the cost of waiting. Plant Vogtle demonstrates this perfectly. The two new reactors, Vogtle Units 3 and 4, were originally expected to cost far less than the final figure and enter service much earlier. Instead, the project suffered major delays and cost increases. The final price tag for the expansion reached roughly $30 billion, depending on how project costs are counted. That number is so large that it changes the entire investment question. At that point, the owner doesn't just need the reactor to work. It needs the reactor to work extremely well for a very long time. Because after spending $30 billion selling, a few $1 million of electricity isn't going to save the investment. The plant needs decades. And this is where nuclear power starts to reveal its other side. A nuclear reactor is extremely expensive to build. But once it is operating, the economics can become much more attractive. A large reactor can produce around 1,000 megawatts of electricity or more. If a 1 gigawatt reactor operated at a 90% capacity factor, it could generate roughly 7.9 million megawatt hours of electricity in a year. That is nearly 8 million megawatt hours from one reactor. Now imagine the plant receives an average realized electricity price of $60 per megawatt hour. That would represent roughly $475 million in annual electricity revenue. At $80 per megawatt hour, it would be around $630 million. At $100, it would approach $790 million. Suddenly, a billion-dollar reactor starts looking like a machine that can generate hundreds of millions of dollars in annual revenue. But this is where we need to stop, because revenue is not profit. The plant still has employees. It needs maintenance. It needs fuel. It needs security. It needs insurance. It needs regulatory compliance. It needs equipment replacement. And if the plant was financed with debt, it needs to pay lenders. So the real question isn't, how much electricity can the reactor sell? The real question is, how much cash is left after everything is paid? This is where ownership economics becomes much more interesting. Consider the hypothetical 1 gigawatt reactor again. Suppose it produces approximately 7.9 million megawatt hours per year. If electricity sells for $80 per megawatt hour, annual gross electricity revenue could be around $630 million. But operating and maintenance costs reduce that number. Fuel costs reduce it further. Taxes and other expenses reduce it further, and debt payments can take another large portion. So an owner cannot simply multiply electricity production by the electricity price and call that profit. The project has to recover its capital investment as well. This is why one of the most important concepts in power economics is the levelized cost of electricity, or LCOE. In simple terms, it attempts to estimate the average cost of producing electricity over the lifetime of a project, including capital and operating costs. But even LCOE has limitations. It doesn't perfectly capture the value of reliability, grid stability, market timing, financing structure, or the fact that electricity prices change constantly. Still, it gives us a useful way to think about the central nuclear problem. Nuclear power puts a huge amount of money into the asset up front, so the plant needs to produce enormous quantities of electricity over a long period of time. This is why the capacity factor matters so much. A nuclear plant can operate day and night, regardless of whether the sun is shining or the wind is blowing. That means the same expensive asset can produce electricity for thousands of hours every year, and every additional megawatt hour spreads the original investment across more output. This is the economic advantage of scale, but there is a catch. A reactor cannot simply operate forever without interruption. Every few years, it needs a refueling outage. The plant shuts down. Fuel is replaced. Inspections take place. Equipment is maintained. Workers perform upgrades. During that period, the reactor isn't selling its normal output, so an outage has an opportunity cost. If a reactor could have generated hundreds of thousands of megawatt hours during a long outage, those lost megawatt hours represent potentially significant lost revenue. This is why nuclear operators spend enormous effort making outages as efficient as possible. The goal isn't just to produce electricity. It is to maximize the amount of time the asset is economically productive. And that brings us to a strange feature of nuclear ownership. The most important number may not be the cost of uranium. It may be the percentage of time the reactor is actually generating electricity. Nuclear fuel is energy dense. A relatively small quantity of uranium fuel can produce enormous amounts of energy. Compared with fossil fuel generation, fuel costs represent a relatively smaller share of total nuclear generation costs. But that doesn't mean nuclear fuel is free. The fuel cycle includes mining, processing, conversion, enrichment, fabrication, transportation, and eventually the management of spent fuel. Still, for the owner, the major economic burden usually comes from the enormous capital investment, rather than simply buying fuel. And this creates an unusual business model. You are effectively buying a machine that is expensive to create, but potentially inexpensive to operate relative to the value of its output. That is attractive, but only if you can keep the machine running. And keeping a nuclear plant running requires something most businesses don't have: an enormous regulatory infrastructure. A nuclear facility has to meet strict safety standards. Systems must be tested. Workers must be trained. Security has to be maintained. Emergency systems must remain functional. Equipment has to be inspected. Records have to be maintained. Regulators can impose requirements that affect how the plant operates. These costs are significant, but they are part of the economics. There is no version of nuclear ownership where you build a reactor cheaply and simply hope nothing goes wrong. The safety system is part of the product. The owner is effectively selling electricity, plus an extraordinary promise. The plant will operate safely for decades, and that promise has a price. Then comes one of the biggest financial questions of all. Who actually pays for the billions required to build the plant? In a regulated electricity market, the answer can be very different from a normal private business. Utilities may recover approved costs through customer electricity rates. Governments can provide financing support, tax incentives, or loan guarantees. Investors can provide equity. Banks can provide debt, and sometimes several of these mechanisms are combined. This matters because the financing structure can completely change the economics. Imagine two identical reactors. Both cost $10 billion, but one is financed with inexpensive government-backed debt, while the other relies on expensive private financing. The reactors are physically identical. They produce exactly the same electricity, but their financial outcomes can be completely different. The reason is simple. Interest is itself a cost of electricity, and when billions of dollars are borrowed over many years, even a small change in the interest rate can create a massive difference in total project cost. This is one of the least visible parts of nuclear economics. People see the reactor, they see the cooling towers, they see the turbines. But behind the plant is a financial structure that may determine whether the project succeeds. And then, there is the biggest construction risk of all: delay. Suppose a nuclear project is expected to begin generating electricity in 2028, but construction problems push that date to 2030. The plant has just lost 2 years of potential revenue. Meanwhile, workers still need to be paid. Loans still accumulate interest. Contractors remain involved, and the owner has to continue carrying the project. That is why nuclear construction delays can be financially devastating. Vogtle is an extreme reminder of this problem. The reactors eventually entered commercial operation, but the journey took far longer and cost vastly more than originally expected. And yet, once the reactors operate for decades, the economics can look different. This is the central tension. A project can be financially painful during construction and still become a valuable asset after completion. That is because nuclear plants have unusually long operating lives. Existing reactors in the United States have received license extensions that allow some units to operate for many decades, potentially reaching 80 years of total operation. Think about what that means. A reactor built today could potentially still be producing electricity when the people who designed its original financing model are long retired. The initial capital expenditure gets spread across decades of production. And this is where nuclear power begins to resemble another type of asset: real estate. Imagine buying an incredibly expensive building. The purchase price is huge, but if the building generates rental income for 60 or 80 years, the original investment can look very different when viewed over its entire life. A nuclear reactor is similar, except instead of renting apartments, it sells electricity, and instead of tenants, it has a grid. But there is one major difference. A building can be renovated relatively easily. A nuclear reactor operates under a much more complex regulatory environment. And, eventually, the reactor reaches the end of its economic life. This is when the final bill arrives. Decommissioning. Shutting down a nuclear plant does not simply mean turning the reactor off. The fuel must be removed. Radioactive materials must be managed. Equipment has to be dismantled. Buildings may need to be decontaminated. Waste has to be handled. And the site must go through a long process before it can potentially be released for other uses. This is expensive, but operators generally plan for during the plant's operating life through dedicated financial arrangements. So the economic life of a nuclear plant has 3 major stages. First comes the enormous capital investment, then comes decades of electricity generation, and finally comes decommissioning. The owner has to make all 3 stages work financially. But there is another issue that can change the equation completely: electricity demand. For years, many developed electricity markets experienced relatively modest demand growth. But now a new wave of electricity consumption is emerging. Data centers, artificial intelligence, electric vehicles, industrial electrification. New manufacturing facilities, and the broader shift away from fossil fuels. All of these trends increase demand for electricity, and large technology companies are beginning to care about something that nuclear plants are particularly good at providing: reliable power. A data center cannot simply wait for the wind to start blowing. It cannot ask an AI model to stop operating because solar production dropped at sunset. Its electricity demand can remain enormous around the clock. That makes reliable generation increasingly valuable. And nuclear plants already have the physical infrastructure to produce electricity day and night. This is one reason the economic story around nuclear power is changing. The question is no longer only whether nuclear can compete with cheap electricity. The question is whether reliable, low-carbon electricity becomes more valuable as total electricity demand rises. If that happens, existing nuclear plants could become particularly valuable. Because building a new reactor can take many years. An existing reactor is already connected to the grid. The land is already developed. The transmission infrastructure is already there. The workforce already exists. The regulatory framework is already established, and the plant can potentially continue operating for decades. That creates a powerful economic advantage for existing nuclear assets. It also explains why shutting down a perfectly functional reactor can sometimes be economically complicated. If the reactor disappears, something else has to replace its electricity. That replacement could be natural gas. It could be solar and wind combined with storage and transmission. It could be another nuclear plant, or it could come from a combination of technologies, and each option has its own economics. This is where the future of nuclear becomes particularly interesting. The industry is trying to solve the problem that has damaged nuclear economics for decades: construction risk. One proposed solution is the small modular reactor. Instead of constructing one enormous custom-built reactor largely on site, developers hope to manufacture standardized reactor components in factories and assemble them more efficiently. The theory is that repetition could reduce costs. The first unit might still be expensive, but if dozens or hundreds are produced, manufacturers could learn, standardize, and improve. That is the same basic economic principle that transformed industries from automobiles to consumer electronics. Mass production can make complicated products cheaper. But nuclear developers have to prove that this theory works economically. A smaller reactor isn't automatically cheaper electricity. If the reactor is smaller but costs more per unit of electricity produced, the economics don't improve. So the real test is not whether small reactors are technologically possible. It is whether they can be manufactured repeatedly, financed efficiently, built on schedule, and operated competitively. That is the business challenge. And it brings us back to the original question: how does anyone make money owning a nuclear power plant? The answer is not by building it cheaply and selling electricity immediately. The business model is much more demanding. You spend billions up front. You survive years of construction. You manage financing costs. You obtain regulatory approvals. You operate the plant at a high capacity factor. You sell enormous volumes of electricity. You control maintenance and fuel costs. You manage outages. You plan for decommissioning. And you need the plant to remain valuable for decades. If electricity prices are strong, financing is controlled, construction stays on schedule, and the reactor operates reliably, the result can be a remarkably durable asset. But if construction costs explode, financing becomes expensive, or the plant cannot earn enough from the electricity market, the economics can collapse. That is why nuclear power has produced both extraordinary successes and extraordinary financial disasters. And perhaps the most important lesson from Vogtle is not that nuclear power is too expensive. It is that the economics of nuclear power are dominated by what happens before the reactor starts operating. Once the plant is running, the story changes. A large reactor can generate millions of megawatt-hours every year. It can operate around the clock. Its fuel costs are relatively modest compared with the value of its output, and its operating life can stretch across multiple generations. That means a nuclear plant is essentially a bet on time. The owner is saying, "I am willing to spend billions today because I believe this machine will produce valuable electricity for decades." That is a very different business from opening a restaurant, launching an app, or building a conventional factory. The investment is enormous. The payback is slow. The risks are unusual, but the asset itself can be extraordinarily productive. And this is why nuclear economics cannot be judged simply by asking how much a reactor costs to build. You have to ask how much electricity it will produce, how long it will operate, what price that electricity will earn, how the project is financed, how reliable the reactor will be, and what happens when electricity demand changes. Put all of those pieces together, and the economics become much clearer. Owning a nuclear power plant is not about making money quickly. It is about turning an enormous upfront investment into decades of predictable energy production. The plant may cost billions. It may take years to build. It may require extraordinary levels of regulation and maintenance. But if it eventually operates reliably for 60 or 80 years, the original investment can be spread across hundreds of millions of megawatt hours of electricity. And that is the paradox. Nuclear power is expensive precisely because it is so complicated. But once that complexity has been paid for, the resulting asset can produce an enormous amount of electricity for an extraordinarily long time. The real business isn't the reactor. The real business is time. And in nuclear power, the companies that can survive the years before the money arrives may ultimately control one of the longest-lived income-producing machines ever built.